Hello, it's my pleasure to introduce Dr. Carlo Lipizzi from Stevens Institute of Technology, and he'll be presenting updates on his research task WRT-1010, Meshing Capability in Threat-Based Science and Technology, Resource Allocation. And with that, I turn it over to you, Dr. Lipizzi.
Hi, thank you, Tyler. So nice to be here. My name is Carlo Lipizzi, working at the Stevens Institute of Technology and with the System Engineering Research Center, the SERC, PI and co-PIing projects primarily for the DoD. In a broad sense. So what we are going to talk about this morning is WRT-1010. There is a project that started about 2 years ago and involved at the peak 30 people, on an average 20 people. And it was a great, marvelous, interesting experience for all of us, and I'm happy to share with you what this is about. So the title, we already mentioned that. The overall idea is basically to leverage on a study that was piloted in 2016 by what was ARDEC and now is a CDCAC on merging logically the traditional capability-based planning and the threat-based intelligence and operational scenarios. So that was challenging because to begin with, how you get information about threats and operational scenarios. You do through text in a broad sense, but at the very end, you need metrics to evaluate the risk somehow, and then inject the risk in your planning cycle. So we decided to integrate somehow the basic process that was defined in 2016 with more analytic capabilities and visualizations without focusing on the super high quality of the visualization. So we didn't want to recreate Tableau. We just wanted to provide an effective way to represent the metrics that we are going to develop. We then introduced additional parameters to make it more usable somehow. And it was in 2 phases. So first phase, fiscal year 18, second phase, fiscal year 19. Initially was, by the end of phase 1, was a proof of concept. We spent a few months trying to really understand how to get a conceptual representation of the problem that can be transformed in algorithms, that can be transformed in code, and can be transformed in something that the sponsor can actually use. So it took us some time. So of those phrases, I just want to drive the attention to the third one. Sun Tzu, The Art of War, know the enemy and know yourself. In 100 battles, you will never be in peril. When you are ignorant of the enemy, but know yourself, your chances of winning or losing are equal. If ignorant both of your enemy and yourself, you are certain in every battle to be in peril. So the core of the whole research is to know better. So to get more information, to do more informed decisions in a domain that is with several layers of complexity. So the project was distributed in 2 years, as I was saying. The first year was focused on acquiring the logic in the planning process, the traditional way, and how other companies were doing planning. We wrote a paper on that, by the way, how companies with longer term planning are dealing with events that can happen within the lifespan of one cycle in the planning. So and that was the problem that we had, that we have, and we addressed with this solution. The second year was basically refine the overall approach and focus on making it somehow usable. There are several issues that we addressed with a team that on an average was about 20 people. Most of the people on the permanent side, meaning more than 50% of the time or permanent anyway. Education, between PhD and PhD candidates, we had the majority of the team members. We used as much as possible resources within Stevens and within the School of Systems and Enterprises in particular, but in general within Stevens. So we consider that an opportunity for our students to do some real-world experience in a challenging problem and environment. The way we work. So we work bottom-up, driven by data, in general, text in this particular case. That seems to be irrelevant, but most of the modeling that we see in system engineering are more of a top-down approach. So we define an environment and then we apply it. In this case, we are going all the way around. So we don't know how the reality is going to be. We don't know what the real model is going to be. The data is kind of driven the modeling phase. So it's bottom up. The second point that is quite a challenge was we are a university. We use most of the people on at the graduate level, as you saw in the previous slide, 2 slides ago, meaning most of them are not US persons, meaning considering we are working in a domain with some levels of restrictions in terms of information that we can handle, we cannot work on the real domain. So that's why we created a proxy domain. Working with the sponsor, we decided to go with the private security industry that is sharing some of the principles with the military environment. It's not a digital twin. I mean, creating digital twins is a project per se. So that was pretty much out of the scope of this project. It's more like a digital relative somehow. So it's related to the actual domain without matching one-to-one. But there is a close relationship between the two domains and a good degree of one-to-one matching in terms of basic needs of the two industries. We developed the systems using an agile approach, starting with low-level prototypes and then moving up. We developed the systems based on components that we developed, like building blocks, like Lego modules. So we created those components that have been used by the systems that we developed. This was also good because it was a way to reduce the exposure of people to phases that are more process-oriented. So we had people, US persons working on the processes, and we had non-US people working on the components. So the components are somehow independent from the domain. So one of the components, it's cleaning the text, just to name one. So that can be done in finance or in military environment. We use a combination of natural language processing in a traditional way for pre-processing, but even the traditional way didn't work well. And at the very end, we realized that we had to develop our own routines, and that's what we did. Plus something a little bit more advanced than the traditional NLP that was based, that is based on transforming the text into vectors, so using libraries like Word2Vec that is doing in Python. All the system is in Python, apart from the routines going to the databases, going and coming from the databases. And then we developed our own methodology algorithm to extract metrics from those matrices. The reality that we want to monitor and evaluate is unstructured and unpredictable. So we are doing a bottom-up approach because we don't know what to expect. The sources are text, but what we need is numbers, not just numbers, but semantic numbers. So statistical numbers are relatively easy to get. Semantic numbers, not much. When you work with text, because text, natural language is natural for humans, meaning that there is a layer of culture, of common knowledge that may not be in the text, meaning the same text may have different meanings for different people or different contexts. Then there is the time factor. So over time, things can change. Even if you use knowledge representation that are specific of the domain, I'm talking about taxonomies or ontologies for one specific domain, the domain can change. People can create their own lingo on the fly. So you need to keep in mind that whatever you use as a base for your understanding, your semantic evaluation of the text, you need to have it able to evolve in time. This evolution per se can provide additional information. So the system that was named Threat-Based Decision System by George Corfiadis, and we all accepted the name gladly and with a lot of enthusiasm. It's a name that is really representing the system. It's composed by two major parts. One is the risk decision support system, and one is the technology monitoring and forecasting. Again, it's about 20 people working on those two systems. The minimum viable product has been released by the end of August of this year. That's what inside. So the number of lines of code do not really make justice of the complexity of a system. So back in time when I was working in software engineering, there was a million different theories on how to measure the complexity of a piece of software. At the very end, just roughly, the lines of code can give an idea of what is inside. Obviously, if the code is in assembler, lines of code is something. If it's in Python, it's something entirely different. So in this case, it's Python, and each line has a lot of functionalities. So it's not one-to-one with the machine function as in assembler or close to that. But we have about 12,000 lines of code, making the system with a certain level of complexity. We use text. Text in particular is under three categories: papers, patents, and news. We had no major problem collecting papers and patents. With news, we started scrapping the news from the regular outlets. Didn't work well, so we had a paid subscription to a service, and we used heavily the news for the technology forecasting that I will talk about in a few minutes. So at the very end is more than 2 million documents feeding the whole system. So one of the key challenges was extracting semantic metrics from text. So again, there is a subjectivity in the text. There is a time factor. How you deal with that. So the example that we use the most, we were doing an analysis of emotions, and we use the classification of emotion by Pluchnik, a psychologist, whose classification is considered one of the most reputable. So there are 6 different emotions with some shades. Joy is one of the emotions. Ecstasy is one of the shades of emotion, of joy. But if you say ecstasy to a narcotic officer, he or she may have a different meaning than a Vatican scholar or a psychologist. So it's the same word, different context, different meaning. So how you take that into account? The cornerstone of both the systems, the technology monitoring and the risk panel, risk decision support system, is the room theory. I worked in artificial intelligence since 1986. At that time, Marvin Minsky and Noam Chomsky were the two leading names in NLP. So Marvin Minsky, while Chomsky was more on the traditional way, Marvin Minsky revised a theory that was developed several years before. That was the framework theory. So he used an example for this theory. When you enter a room, you know right away if it's a bedroom, if it's a living room, or a dining room, or a bathroom. Not because there is a label saying this is a bedroom, but because you have a mental framework resonating with the information that you get from your eyes, from your vision. So I used this example to rename the approach as a room theory, adding to the framework theory a computational layer transforming the corpus representing the knowledge of a given domain in a computational way. So we transform using vectorization methods a large corpus representing the domain that is the point of view that we want to have, and then we use that for the evaluation that we want to do. Basically, this room theory is working this way. You have the room that is the computational representation of the knowledge base. So you first collect a huge quantity of data. If you have time, check my presentation later in the afternoon. For another project, we use the same theory in another specific case that was only focused on the application of room theory. I mean, this project that we are revising now is a little bit more complex, and there are other parts. So that one was just on that. It's a real application of the theory. The project is WRT-1023, and it's going to be 4 o'clock probably in the afternoon. Just check the program. So you have the room representing the domain, can be the military domain, can be the technology, can be a given technology. Then you have documents. So this room is basically a huge matrix with all the words in a broad sense, and a bunch of numbers. That is I mean, each word has n number, meaning each word is a vector, meaning is a point in space. So then you have the documents that you want to analyze. You take each one of the word in each one of the document, and you compare those words with keywords that are in this benchmark. So we basically had 3 levels of benchmarks, one for technologies, one for companies, and one for market sector. So you can see how you can map those 3 that are for companies, for a security company in the military environment. And then you basically do a lookup in the table in the room to get the vectors for each one of those words, and then you calculate the distance. Calculating the distance will give you the relevance of, I mean, that benchmark, that keyword in the document that you are analyzing. You add up somehow, then there are some refinements on that. You add up all the words, I mean, all the distances for all the words in the document with each one of the benchmarks, and you have, and then you normalize, and then at the very end you have a number that will tell you the proximity somehow of each document with each one of the benchmarks. So that's the way it's working. Then the information flow that is, I mean, feeding somehow the old system. So we have 3 sources, again, news, patents, and papers. Then, because they are unstructured, we use a non-relational database to dump the information, is MongoDB in this case. And then every longer life cycles, we generate the rooms, meaning those matrices that are, I mean, incremental somehow. So we build on top of what is already there. And then we use the more recent documents to be analyzed. So there is a heavy pre-processing that seems to be trivial, but it's not. Just to give you an example, system engineering, weapon of mass destruction are engrams. So you want to be sure that you use the same engramming method for each step of your process, because otherwise it's not going to work. The current engrammers are either very slow but accurate when you work at the character level, or non-accurate and relatively fast. So we built our own engrammer that is faster and is good enough for what we need. Let's talk a little bit of the applications using one of the, so we were on the information flow. The technology monitoring has a basic function to be a sort of radar screen for new technologies, meaning you know what the current technologies are, but you may not be aware of a technology that is emerging. So you want to have a radar screen for those new technologies coming and then being alerted. But then the idea was, why don't we try to do a little bit more and to see if we can predict technologies? So because we basically have numbers, those matrices, you can have matrices in time and analyze how the technologies that are mapped by those matrices are evolving in time. So we follow two different approaches. One is using network theory. So each matrix can be represented by a network. Then you have one network for each time, that can be each year. And you can use the morphology of the topology of the network and the evolution of the networks to predict the network at the next time. This will not give you the name, obviously, of the new technology, but will give you the name of the technologies that are somehow related to create a new technology. So the basic assumption is that most of the technologies are kind of consistent with the past. So you can, if you consider smartphones, you have regular phones, you have the PDAs that were in the previous generation, you have antennas, you have batteries. So even if you didn't know that there was a smartphone coming, you would see a sort of convergence of those technologies. Then you can also do on the application, on the sectors. So if you consider GPS, initially was for military uses, then for navigation, then for marketing. It's the same technology moving across different sectors. So one is based on networks, and one is based on analyzing those matrices in time. So those are some of the use cases. So what if analysis on the overall competitive scenario? What are the strengths and weaknesses of the players? How this scenario would be impacted if I give up one of the technologies? How can I decompose technologies in their key components? So the kill chain for the technology. Role playing. So we will see that in the demo in a minute. Then the horizon scanning is quite obvious. This prediction of technology, I mean, the future cannot be predicted, but can be estimated somehow. So how those technologies are related to these coming technologies, to the technologies that I have. So let me go now to here and do a little bit of a demo of the two systems. We don't have a lot of time. We have a little bit more than 5 minutes, but I just want to give you an idea of how the systems are working, hoping that they will not crash using VPN. I mean, I'm in the Catskills. The connection is decent, but sometimes it's not as fast as it should be. But anyway, so that's the risk panel, the risk DSS. So you have several tabs. So this has been developed using Python and a library called Dash that is both commercial and open source. We used only open source software. So this is the open source version that it's not as fast and as stable as the commercial, but it's working fine. So you can select who you are. So in this case, it's this company. We can change the company. I don't know, Palo Alto Software. We can get, that's the case where it's not working. So you have the technology portfolio for the company, and you have the comparison between that company, the technology portfolio of that company, and the major competitors. So you have, those are the major competitors for this company. You have two views, one that is based on this competitive or comparative analysis of the technology. And this one that is leveraging on the concept that originally was created by Warren Buffett on the moat, financial moat, based on the competitive advantage. We calculated the competitive advantage primarily with a combination of time a company is in one technology and market share for the same technology. So there are two views. When you set one company, then you can do sort of a comparative analysis. So that's where your company is compared to the others. And then the technology is focused on those sectors. So then if you pick, and this is the distribution of the technologies for this company. If you say, I want to divest in, I don't know, let's say information protection, this will change your position. Then the other panels are more on the general competitive market. So you can define your risk profile, just you do when you do wealth management. If you want to defend, if you want to offend, based on the choices that you do, you have a recommendation on the different sectors where you may want to invest. And you have this gauge just telling you for each one of the technologies where you are hovering on, if it's way too late or other. And for each one, you have what is the stage of the technology, what is the coverage for the technology, and what is the market environment. Then you have a little bit of details on how the metrics are applied in this sector. You have a little bit of view of what's going on in terms of acquisitions, and some information about the implementation of the technologies. On the technology monitoring, so the user defines what are the technologies that are the baseline, so the technologies that are currently used. And then based on that, and based on the evolution that we have in the news papers and patents, those are the technologies that are closer. It's a sort of correlation matrix, and the technologies that are emerging. Then you can have details. You can compare the life cycle of different technologies. For each one, you have the persistency of the technology, then how they've been applied. I mean, in this case, there is not much biometrics and controller, but eventually you have the comparison per sector. You can create networks of the technology. So this is basically behind the idea of the kill chain. So you can select whatever is your technology, and eventually you can move it for a better view. You can select one and change how technologies are related to older ones. And you can have some parameters on the network to determine, what is the most relevant. On the upcoming technologies, again, we have two major approaches. This one is based on the network analysis, and this one is based on the analysis of the matrices. So you have artificial intelligence in 2017 that was close to Drone Warrior, Office, and all the way the prediction is being close to the police department, things like that. So those are not integrated. They are still at this level. So or at this level. So you have just the code that is working, but it's not integrated. And then we have a user interface for the user to drop their documents. So let me conclude the presentation with some final slides. What's the difference between our solution and commercial solutions? So this is applied research and is optimized for the need. In my opinion, the key difference is the last point. No available commercial solution is able to analyze text by extracting semantic insight based on predefined point of view. So there are two assumptions here. One, semantic insights, so the semantic metrics, and the second, defining the point of view. Then we have some ideas on future developments. I mentioned some of them. And new capabilities, so creating a sort of DNA for the opponents, the technology footprint, working on a new room theory using a more advanced way to create the matrices. We are thinking about basically quantum theory and transforming the points into functions, but that's something we can discuss in another moment. And then creating scenarios for technology alternative evolution, meaning you see the evolution, but sometimes you see a gap. This gap is probably because someone has the technology, but there is nothing in the radar screen, meaning nothing in the news, in the papers, in the patents. Because it's proprietary, because it's something that for them is a competitive advantage, and they do not want to release it. So it was a great opportunity for us. One keynote, and that's my final one, developing machine learning AI system is developing a system, meaning all the concept of system engineering, software engineering, and development operations need to play a central role. So that's really essential. We have a website that is NLP Lab. So this is who we are. That's the team. You can get more information clicking in the links. That's how we work. That's some of the samples, basically the same visualizations that you saw in the live system. The systems were running live in a server by the CERC website server. So that's basically it. I really thank you. I'm sorry if I left just 1 minute for a Q&A. Let me go back here and let me stop sharing somehow. And I'm ready.
Thank you very much for your talk today, Dr. Lipizzi.
Thank you.
There were no questions in the chat section, but perhaps someone will reach out over email or something like that.
Absolutely.
Thank you again. The room will end in 1 minute, and the next track will start in 6.
Thank you.
Thank you.